Now that we have Fourier transforms, I'd like to solve the previous circuits that we looked at using Fourier transforms. What the Fourier transform will do is I'll get the same answers that I get using Circuit Lab, only with a lot more effort. So as a recap, we had a buck converter that we analyzed 2 lectures ago. What we did is I had an input, V1, that wasn't a sine wave. What we did is we changed the problem so the input was a sine wave. It kept the flavor of the same problem, had the same DC level, same frequency, same peak-to-peak voltage, but was slightly different. The answer that we got was close, but slightly wrong. If you want to get the exact answer, then you need to use Fourier transforms. With Fourier transforms, you don't make any approximations. Given an input that's periodic, I can express that input exactly. The problem with Fourier transforms is it's a lot harder to get slightly more accurate answers, but you can do it. For example, going back to the buck converter, actually the AC to DC converter, the voltage at V1, which is really all I care about, is a half-rectified sine wave. Given that, find the voltage at V2. In this part of the circuit over here, this is a full bridge rectifier that we cover in electronics. From now, we don't care. The circuit doesn't care how you generate V1. All I care is given V1, find V2. The approximate solution that we did 2 lectures ago was take the input, treat it as a DC term. This matches the DC term of V1. Add an AC term. This is the same frequency, 120 Hz, same peak-to-peak voltage. So this is almost the same problem. The nice thing about this is I changed the problem to one that I can solve. And here I get a DC term and a 120 Hz term. That'll almost be correct. If you simulate it in Circuit Lab, you'll find the answer is close, but a little bit off. The reason it's a little bit off is this approximation. Using Fourier transforms, I can avoid that approximation. What I do with Fourier transforms, like we mentioned in the previous lecture, given V1 of t, I can decompose it into the first harmonic, second harmonic, third harmonic, fourth harmonic, and so on, plus a DC term. Once I find V1 using its Fourier series approximation, I can now analyze using phasors. Treat this as 5 separate problems, one at DC, another one at 120 Hz, 240 Hz, 360 Hz, 480 Hz. Add them all up, we'll get the total answer. To illustrate that, take the DC term. The first term was 11.331 volts. Analyze the circuit at DC. The inductor becomes J omega L. Capacitor becomes 1 over J omega C. The input is 11.331. Solve using voltage division, and I get 8.716 volts. That's the DC term. Next, solve with the first harmonic, 120 Hz. Here the input is minus 8.488 plus J0, minus 8.4 cosine, 0 sine. The inductor goes to J omega L. Capacitor goes to 1 over J omega C. Put these two in parallel. I get 63 minus J48 ohms. Do your R1 over R1 plus R2 times the input, and I get a complex number. What that means, this is the cosine and the sine term at 120 Hz. Next, analyze the 240 Hz. At 240 Hz, the input is minus 1.68 plus J0, minus 1.698 cosine, 0 sine. The inductor becomes J omega L, capacitor becomes 1 over J omega C. Put these in parallel, use voltage division, and I get V2. What V2 means is 0.052 cosine minus 0.038 sine. Repeat. Analyze at 360 Hz. Again, I've got the input at 360 Hz, or I misspelled 360. The inductor, J omega L, capacitor 1 over J omega C. Put these in parallel, use the voltage division, I get V2. Repeat. At 480 Hz. Again, I misspelled 480 Hz. Here's the input, minus 0.404 cosine, 0 sine. Inductor becomes J omega L, capacitor 1 over J omega C. Put these in parallel, do voltage division, yada, yada, yada. When all is said and done, what I have is the input, the first harmonic, second harmonic, third harmonic, fourth harmonic. Put them all together, that gives you the red line. That's exactly what Part Sim gave you, exactly what Circuit Lab will give you. That is the exact solution. What we had before was almost right. There's a phase shift. The reason the phase is off is because I don't care about phase when it comes to AC to DC converters. I just kept the same ripple, kept the same DC voltage, kept the same frequency. The time shift I didn't care about, hence the time shift is off. But notice the approximate solution is almost right. This is the exact solution. Hence, with Fourier transforms, you can solve a circuit with any periodic input. That's the power of Fourier transforms. Any circuit that has a periodic input, I can analyze. The work that you have to do is a whole lot harder than it is than what we do in electronics. And also note, if you look at the output, this is almost a pure sine wave, red line. But look at these terms. If I ignore the second, third, fourth, and so on, my answer is almost right. That's the saving grace in electrical engineering. Most circuits have a DC term, and the first harmonic really dominates the response. If I change the problem and just treat it like a DC term and the first harmonic, I'm 90, 95, 99% accurate in getting the output. That last 1% is a great deal of effort if it's worth it. If you want to find out what that actually is, simulate it or go through all the effort. If you don't care about that 1%, just the DC term and first harmonic is usually plenty good. So likewise, the Fourier series in theory says I have to go out to infinity. In practice, all I need are two terms typically, the DC term and the first harmonic. That's Fourier transforms. You'll see more of this when you take 343 signals and systems. We're covering that now because once you have superposition, you really have Fourier transforms.